Hi everyone and welcome back to Life Technologies YouTube channel. I hope you're doing well and thank you so much for watching this video and also continuing to support our channel. So this is another episode of our IPRAN training series, and in this session we are focusing on how to perform service test on IPRAN network. So sometimes I've received so many requests. Someone is managing a network and they are having some weird issues, and we've had to help them to troubleshoot these network issues. So once you've set up your network, you've done the hardware installation, you've done the powering of the devices, you've done the software upgrade, maybe if it was required, you've done the service configuration on these nodes, you've integrated the nodes to the NMS, you've also done the configuration on the controller side. Now it's time to perform some service test to ensure that everything is working okay as expected. And if there is any issue that will be identified that is affecting the customer experience, then you will have to do some optimization on this network. Remember, network deployment is a continuous process. You do the setup, you do the configuration, you do the service configuration, and you do continuous testing. You do continuous analysis of the network just to ensure that you have a network that is operating optimally, you have a network that is reliable, that is redundant, and you also have a network that is providing the best services to the customer. So that is the goal of us doing some tests, just to ensure that our network is operating as expected. And if there is anything that will be identified, maybe the customer has some complaints, there are some call drops, there are some packet drops, or there is some devices that are not able to communicate with any other device in the network, then we need to go ahead and do some troubleshooting. We need to go ahead and do some optimization on this network so that we are able to improve on the customer experience and improve the efficiency of our network. So that is the goal of doing service test on the network. And before we start this session, just a kind reminder that if you are watching this episode and you are yet to subscribe to our channel, kindly do subscribe to our channel, and also remember to like, comment, and share with your connections. So we've done multiple episodes on IPRAN. We started with the general architecture, and we are still maintaining the same architecture from the RAN side, having the BTS, the base station, and then you have the CSGs in this topology. It's represented by the UPE. You have SPE, the aggregation nodes, and then you have the NPE, the RSGs. And the RSGs are connecting to the controllers, the different controllers in the network, maybe BSC for 2G, RNC for 3G. You could be having the Evolve packet core, or even you could be having the 5G core. So once you've done that setup, you've done the installation, you've done the configuration, you've done the software upgrade required on the network equipments, you've done configuration on the controller side. Now it's time to do some tests just to ensure that everything is operating as expected. We don't have any issues on the network, and if there are any issues identified, that is the right time to do optimization, and you will continue doing it back and forth just to ensure that we have the best network for our customers that depend on this network. So you need to perform some tests. You need to do some service test, you need to do some ping test to ensure that everything is communicating with everything else. You need to do some traces to ensure that the service flow is as expected. You need to do some checks on the physical links to ensure that our transmission network doesn't have errors. Because if we have errors, if we have packet drops, then we have issues in the network that we need to fix. So the reason I'm doing this video is because I've received some requests from some of you, and they are always like, oh, I'm experiencing this issue. How should I fix it? What should I check? What are some of the checks that you need to perform? What are some of the things, the common signs and symptoms that there is an issue in the transmission network? So of course the focus in this video is on the transmission network that we've built, the IPRAN network that we are configuring services to run on. So in this video, we'll just be highlighting some of the basic checks, and of course there are many. you will have to do some drive test from the radio side and many other, maybe from the controller side, but our focus will be on the transmission network, our IPRAN network that is carrying these services from the BTS to the controllers. So we are using the same topology, and we've done this implementation before. We've done the protocol configurations in our previous episode. We've also highlighted some design principles of how to do this protocol design from ISIS, BGP, MPLS. Remember, all those steps are very critical, because if you miss one of them, then you will have issues in the network. If you don't design your IGP protocol, ISIS, correctly, if you don't do proper design of your protocols like BGP, if you don't do proper design of your IP addressing, then you expect to find issues in the network once you've deployed the services. So it's a systematic process that you need to follow from the design phase to the implementation phase, to the testing phase, to the maintenance phase. There are some things that you need to pay attention to and ensure that you do them correctly. So we've already ensured that we have the protocols running. If I go to the topologies, so we have the ENSP topology that we've been using. If you check some things like the BGP display, BGP, VPN, V4, all peer, you will see that we have BGP peering sessions towards the RSG, the NPE, and also towards the CSG, the UPE. If you display ISIS peer brief, you will see that we have ISIS adjacent these on these nodes. It's already configured, it's up and running. If I display IP routing table, I should be having my public routing table populated with different routes towards different destinations. If I check my BGP VPN v4 all routing table, I also expect that I'm having some VPN v4 routes. Remember, this is MPLS network, so we are doing BGP MPLS VPN. So you can see that we have different routes in different VPN instances for different customers. And even on the UPE, we expect that we are having the same. So I can do display BGP VPN v4 all peer. You see that we have the peering session, display IP routing table. We have routes in our public routing table that should help us to access different parts of the network. And then we'll be having our display BGP VPN v4 all routing table. You see that we have the routes in the relevant VPN instances or virtual routing and forwarding. You can also check for specific VPN, so display IP routing table, VPN instance to GVPN. So you see that we have the routing table for the to GVPN. We've received a default route from the ASG, and that is expected. So you need to do some of these tests. You need to do some of these verification just to ensure that everything is okay on the network, everything is running as expected, and we are not having anything that is not correct, that will cause problems when we start carrying customer traffic. So let's look at some of the tests that you need to do, starting with the very basic test that you can perform, and these are mandatory. You must do this test. Don't just assume that everything is okay. Don't just make assumptions that, oh, my customers are able to browse, oh, I'm happy, everything is okay. No, you need to do these tests to ensure that everything is working as per the initial plan. So from the first one, you need to do some bidirectional ping tests. So bidirectional ping test will help you to see whether, remember, communication is bidirectional. When you are on this BTS should be able to communicate with the controller. The controller should also be able to communicate with the BTS. Sometimes there are weird scenarios. You find that you can ping from the BTS towards the controller, but the controller is not able to ping backward from the controller side to the BTS. You find that you are on this SPE, you are able to ping the UPE, but the UPE is not able to ping the SPE. So you need to do some bidirectional ping test from the RAN side towards the controller, because we've already confirmed that our transmission network is okay. The protocols are running okay. We now need to do the end-to-end service test from the BTS the radio access network side to the controller side and even to the NMS. Remember, in a service provider network, we will have a BTS somewhere here. I mean, an NMS that is used to manage the transmission network. We have an NMS that is used to manage the BTS and other radio side equipments. So you need to have bidirectional communication between those different equipments on the network. So for the ping test, I've said that you need to do bidirectional. So from the BTS, we can do ping test towards the controller side. From the controller side, we can do ping test towards the BTS and just ensure that it's working okay. We don't have any packet drops and even the latencies are okay. So those are some of the things we are checking: latency, jitter, packet drops. So when I look at this display IP interface brief, you see that we have this interface here, configure 10.160.10.2. I can display ARP. So you can see these are local IPs, but of course we have to initiate some pings for us to be able to learn the remote IPs. So I'll do ping -a. Remember, we haven't advertised the point-to-point IP towards the controller. So that's why we need to source from the local IP. So it's 10.160.10.2. And then we need to ping. Maybe you want to do some 100 packets. You use count, and then you can do the destination IP. So this is the IP that is configured on the controller side. If you check on this core switch, display IP interface brief, you will see that we have this 1090 10.1 for the 2G services. So what I need to do is I'll continue with my ping. I'll do the ping from the BTS, and you can see that we are able to ping. You see the TTL value, you see the time it takes to get the replies, some 120 milliseconds. So the timers are okay. We see the reply is coming from 10.90.10.1, and we wait for it to complete so that we can be sure that we don't have any packet drops, we don't have any packet loss on this network. So sometimes, of course, when you are doing the ping, you can always do the rapid one so that you save on time and it will be faster and saves time when you are doing the ping test. But for this case, I'll just leave it to run and complete. It's just 100 packets, so it should be within some 1 or 2 minutes, it should be completed. So this one confirms that our communication from the BTS to the controller is okay. You can see that we've sent 100 packets. We've received 100 packets. 0 packet loss. And you see the round trip, 60. The average is 103 and maximum is 150 milliseconds. So this is okay. This is accepted. Of course, this is a simulation environment. So you don't expect to get maybe weird figures or the figure that you may be getting in your real network. So there will be some variation. So once we've done from the BTS to the controller, we can also go to the controller. And from the controller, I need to ping -a 10.90.10.1. I'll be pinging with the 100 packets also. And then I need to specify the destination IP. So this is 10.160. If we check on the UPE, on the BTS, this was BTS 01. You see that we are having display IP interface brief. We have this 10.160 10.2. So 10.160 10.2, that should be the IP, and you do the ping. So this one now, you can see that we are doing a ping from the controller side towards the BTS. And we expect to get similar, almost similar results as the one that we did from the BTS towards the controllers. So you should do bidirectional ping test just to ensure that everything is okay. And once you've done this, we'll be moving to the next step where you also need to do the trace to ensure that there is symmetric. The symmetric path is used for both uplink and downlink. Remember, there is traffic that is sent from the BTS towards the controller and the downlink traffic from the controller towards the BTS. It should be using the same path to avoid any issues, to avoid any latency issues, to avoid any retransmission of packet. It should be using a symmetric path from end to end. So let's check our ping from the controller to the BTS, and you see that also we have 100 packets transmitted, we have 100 packets received, we have 0 packet loss. If you have any packet loss, it could be 1%, it could be 2%, you need to check and fix that issue. And this one could be due to maybe they are degraded links, there could be some links that are congesting, there could be some loose connections in the network. So you need to be able to establish what is causing the packet loss in the network and clear it. So what if you are not able to ping? Many times you find that you have a BTS here, but this BTS may not be able to ping the VPC, or the VPC is not able to ping the BTS. One of the basic things that you need to do or to start with is, are you able to ping the BTS from the UPE? Because remember, this UPE is the one that has the gateway towards the BTS. So are you able to ping from the UPE to the BTS or the BTS to the UPE? So you also do bidirectional pings. If that's not the case, then it means you have a local issue between the BTS and the UPE. If you can ping it from the UPE and then you can move to the SPE, are you able to ping that IP from the SPE? Is it available on the SPE? Do we have that IP advertised towards the SPE? You log into the SPE, you display IP routing table, VPN to GVPN, and ensure that you have that route advertised. So you can see that we are having it here. This one 10.160.10.0/29, and it's coming from 1.1.1.5. So this one confirms that we have the route. Go back to the NPE. Are we having that route advertised to the NPE? Display IP routing table, VPN instance to GVPN. If there is anywhere that we are missing that route, it means we have an issue in the end-to-end communication, and you need to check and fix that. So you can do it segment by segment and ensure that you have end-to-end communication from the BTS to the VPC. So you do this for all the technologies, 2G, 3G, 4G, 5G, O&M. You do it independently just to ensure that everything is working okay for every technology. So those are ping tests. You do it bidirectional, and you can do more packets. Don't just do 5 packets. 5 packets may not be able to capture the issue. So you need to do it for more packets, maybe 100 or 1000, so that you can see if all the packets will be transmitted and you will get replies okay. So the next thing that you need to check is on the bidirectional trace routes. So I've mentioned that one of the things that you need to ensure is that we have symmetric paths for the communication from one node to the other. If we are having traffic flow from the BTS using this path, then we should also have the traffic flowing from the VPC to the BTS using the same path. Asymmetric routing will always have issues because remember, one path may be faster, another one is slow, one is congested, another one is not. So you need to ensure that we have symmetric routing in the network. If one direction is using the upper path, for example, if we have BTS1 going directly to the controller, the other side should also be the same. So we can do trace route just to ensure that we have similar path that is used for the downlink and uplink forwarding of traffic. So we can do trace route and we'll do it from both sides. So I'll just keep the drawings. I'll go back to the screen, go back to BTS01, and I need to trace, was it BTS02? It was BTS01. I'll trace again -A. This is 10.160.10.2, and I'm tracing 10.90.10.1. So we expect that the path should be symmetric from source to the destination. So sometimes, of course, when the traffic is going through the transmission network, some path will not be shown on the trace. So you can see that we have the gateway 10.160.10.1. It's there. So from the BTS, the traffic is hitting the gateway, which is 10.160.10.1, that is on UP01. And then this is in the transmission network. We are not seeing the hops, and that is expected sometimes because this part of the network doesn't have information about those destination, maybe the source and the destination in the public IP routing table. So the hops will not be shown. But you can see that it hits 172.16.16.0, which is on NP1. So on NP1, if I display IP routing table, IP interface brief, you expect that you have this IP. So 172.16.16.0/31. It's in our trace, this trace. And then this is on the switch. So on the switch, if I display IP routing table, actually it should be again IP interface brief, you see that we have 172.16.16.1. Go back to BTS01, you see that this is the hop, the fourth hop. And from the fourth hop, of course, it's now hitting 10.90.10.1. So that is expected. You go back to the core switch. So from the core switch, we also want to trace the downlink traffic. So I'm tracing -A 10.90.10.1, and I'm tracing 160. This is 10.160.10.2. So we expect that it should be following the same path. And you see that here, it's hitting the gateway. And then this is the IP that is configured on UP1. And then we have the IP on the BTS that we are trying to reach. So it's also using the upper path. From here, so from the BTS, it hits the gateway that is configured on the UPE and then goes straight to the NPE. Of course, remember we have LSPs or MPLS tunnels on this MPLS network. So from here, it hits the switch. When it's coming back, same. Hits the gateway on the NPE, flows to the gateway on the UPE, and then to the BTS. So if you find that you expect the traffic to flow this way, but it's not. It's not flowing this way. It's following another different path. Then you need to find and fix the issue to ensure maybe there is cost metric that you've configured incorrectly. Maybe there are some paths that are not accepting, or maybe you haven't implemented MPLS on some links, which means you are not receiving routes on that path. So you need to do proper analysis on the network to ensure that you have symmetric routing. The uplink and downlink should be using a similar path, and then you should be okay on the network. So another thing that you need to check is on the physical port. So for the physical port, you need to ensure that you don't have any errors on the ports. The ports are not flapping. The ports are stable. The physical connection between the devices, the protocols are not flapping. If you have such issue, then it means your network will not be reliable. You will be having packet drops. You will be having some errors reported, and that one will affect the operation of your network. So this is very straightforward. You just need to check on the physical ports. You can check on different segments of the network. From the UPE, you can check the port that is connecting to the BTS. So if I display IP interface brief, you will see that we have this port. This is gig 002 that is connecting to the BTS. You can display interface gig 0/0/2. You see that let me display IP interface gig 0/0/2 so that we get more details. So you can see that from here we can be able to see, I don't know whether this one will allow us to see the packet drops, or you see we have dropped packets. Do we have error information? So you find that in the simulation environment, we may not be able to see the error information. But again, on our real networking devices, you'll be able to see those details. So you can do this across the network on all the nodes that are involved in the forwarding path. Once you've done the trace, and again, not just the one that are the active path, you also do it on the redundant path so that whenever there will be a switch in the traffic, you won't be having issues in the network. So this one should be done end to end on all the network equipment that are in your network to ensure that you don't have errors, you don't have packet drops on the links. So you do this across the network from the UP to the SP to the NP, and also the BTS should also be checking. The run side, they should also be checking such issues. Even on the controller side, you may not be having errors in your transmission network, but you may be having errors on the interface, on the BTS or on the RNC or the BSC. So you also need to do that checks. So the next check that you need to perform is link redundancy test. So we've built a network that has redundant links. If you check on this network, you see that we have redundant paths. We have a ring setup. So what we want to do is to ensure that when there is a link failure, our traffic is flowing okay. So from UP1, you see that UP1 traffic can be forwarded to SP01, or it can be forwarded to UP02, and then it will find its way to the controller side. So you need to do the link redundancy test. Ensure that your ring is working okay. So this one you test by shutting down, you manually shut down the interfaces or you disable protocol. Many times I prefer to manually shut down the links so that the link is down 100%, and then you can see the traffic flow. So of course, when you are doing this, you're expecting that traffic should be able to switch over to the secondary path. And it should be able to flow without any issues. No packet drops again, no errors on the links. So when you log into the router, let me go back to BTS1. From BTS1, I'll do ping test of 1,000 packets. And once I start my ping, I need to log into SP01. We are expecting that traffic is flowing from UP01 to SP01. So I log into SP01 and shut down the interface gig 00 that is connecting to UPE so that traffic should be able to switch. Interface gig 0/0/0. I'll do shut down. So I've shut down the interface from UP1 to SP01. We expect that traffic should be able to flow the other way from UP1 to UPE2 to SPE2 and then to the controller side. So let's check our ping. So on BTS1, you see that the ping is still going okay. We just had one packet drop when there was traffic switchover, and that is okay. But we haven't experienced any other downtime. So the downtime has been minimized because we have redundant path, and you expect that traffic is now flowing through this link. So when I do a packet capture on this side, I expect that that is the path that my traffic is taking from there, and you can see that we are having the pings going through that link. Again, that one confirms that the traffic switchover is okay. And again, you can still go ahead and shut down another link, maybe on NP02. On NP02, because you're trying to isolate all the possible issues that could cause traffic impact whenever you have multiple, because sometimes you may be having multiple links down, not just one. You could be having 2, you could be having 3. If you have multiple links connecting different devices, because you cannot determine where the link fault will happen. So I can do 002, I can do shutdown. So we've shut down the link between these two. We still expect that our traffic flow should not be impacted. So on BTS01, you can see that our ping is still okay. Again, we lost one packet, but the ping is still okay. So traffic is able to flow from BTS01 to UP1, UP2, SPE2, SP1, NP1, and then go to the controller side. So this one confirms that we have redundant link. The redundant is working okay. If there is a link failure in the network, we will be okay. We don't expect to have downtime, or we don't expect to have manual intervention to switch traffic to the redundant path. And remember, that is the essence of having dynamic routing protocols like ISIS that we have deployed on this network. It should be able to dynamically adapt to the network changes. So we've shut down this link, we've shut down this other link, traffic flow is still okay. No issue experienced, no downtimes, no service impact. So I will restore these links. And once we restore, of course, we expect that traffic should also fail over. Go back to NP2, undo shutdown. So after some time, we expect that once the protocols are established, traffic should be able to flow back through the primary path. So of course, it takes some time to switch over for the network to converge, and then we'll have traffic failing over to the other path. You can see that now we don't have any hello mess. We don't have any ICMP messages on this link. We are only having OSPF packets on this link. All our traffic has switched back to this primary link. When you do a packet capture, again, you expect to see that we have ICMP packets traversing that link. And that is how it should be. And that is how you test the link redundancy in a network. So, another thing that you need to test is node redundancy. Because sometimes there could be power failure, sometimes there could be a node becoming faulty, or maybe you just have like a weird scenario where there is fiber cut and maybe these fibers were using the same duct, so you've lost the connection to G01, G02, G00. This node is isolated, which means these should not be used on these links should not be used when forwarding traffic, because this node has been isolated fully. So when that one happens, it means there is node failure kind of issue, and you need to switch traffic to the redundant path. So we can demonstrate that by shutting down all the links on these SP2, SP1. Remember, the traffic is still using the primary path. So what we'll do is we'll shut down all the links on this node just to verify that everything is working okay. I'll go to interface gig 0/0/1, also shut down. Go to interface gig 001, 002, shut down. So I've shut down the 3 links that are connecting to SP01. So SP01 is isolated at the moment, and we don't expect to have service impact because you see we had just packet drops, maybe 1 or 2, but the service flow is still okay. We can still communicate from the BTS to the controllers. The controllers is also replying without any problem. There is end-to-end communication via the other path. When you check on UP1, display BGP VPN v4 all peer, you see that yes, this BGP, of course, it will take 180 seconds to go down, but our service is still flowing through the redundant path that is available. So I'll restore the link. So some of these links, of course, they're overlapping, but again, you can still do it individually or you can combine them, because when you do this, you've isolated the node, you've also isolated multiple links. So you've tested link redundancy and not redundancy, which is okay. So I'll restore the links, undo shutdown. You need to go to interface gig 001, undo shutdown. gig 00 undo shutdown. So we expect that display SIS peer. We expect the SIS peer to come up, display BGP VPN v4 all peer. We also expect that the BGP session should be restored. And then traffic should switch back to the primary path that was being used before. So that is on the link and not redundancy test. Another thing that you can do, remember, when we are designing BGP for IPRAN, we normally have multiple peers so that we have one that is redundant, one is primary, another one is secondary, and they are all advertising routes towards the UPE, and the UPE is selecting the most optimal based on the BGP path selection criteria. So you can also test the peer redundancy. You shut down one peer and check, are we able to forward traffic through the other link? So this one is also another test that you should do. So on this, if I do BGP, the S number is, let me just display current configuration BGP. See that we are on a 65008, so BGP 65008. Display this. Let's see whether we can. So do peer 1.1.1.5, use a question mark. Do we have the shutdown or disable command? Where is it? So we do ignore. We have the ignore command. So once we do the ignore command, when you check on, let's first go back to UP1. If you check BGP VPN v4 all routing table, you will find that we are having two default route, one coming from 1.1.1.3 and another one coming from 1.1.1.4. So it means we are receiving the paths from different BGP peering sessions. I can do VPN instance to GVPN and do 0.0.0. I need to do the routing table. So I'll do routing table 0.0.0.0. You will see that we have two, one from 1.1.1.3, another one from 1.1.1.5. So we are disabling the BGP peering to SP1. So when I do ignore, we expect that the BGP session will go down. On the UP1, you see that the BGP peer went down. If you do this, now you find that we have only one default route coming from 1.1.1.4. If you go to BTS1 and do the ping test, you see that we still have bidirectional communication from the BTS to the controller. So you can again test the NPE. Are we able to get the routes correctly from the NPE? Are we able to get the routes correctly from the NPE, NPE1 and NPE2? So that one should be done individually for all the different nodes, especially if you have a route reflector. Am I able to work with one reflector like you have RR1 and RR2? Am I getting all the routes from RR1? Am I getting all the necessary routes from RR2? What if I lose RR1? What if I lose RR2? So I need to do such tests to ensure that whenever there is an issue, whenever I'm losing BGP connection to one peer, am I still able to forward traffic without any challenges? Am I experiencing some service disruption when I'm losing BGP peering session towards some nodes? So you need to check on that, and you've seen that we can use the ignore command. So I can do undo peer 1.1.1.5, ignore. And again, I've mentioned that you can go ahead and test for all the other BGP peering session. If you have a route reflector, you can also check. These ones was .5. I do display BGP VPN v4 all peer. You see that it's still idle. It will take some time. check again. So it will take some time for it to restore. So the BGP peering session has restored and now everything should be okay. So you need to do BGP redundancy tests. Another thing that you also need to check is on the routing table check. So when you are checking the routing tables, ensure that they are also receiving all the necessary routes. Are you getting all the routes that are expected to be used to forward the traffic on your network? So you just display IP routing table, that VPN instance that should be able to close on this one. So for example, I can do on NP, am I able to get all the routes? I just do display IP routing table for the public routing table, or I can display IP routing table, all VPN instance, and I should be able to. So this one doesn't work. Let me see the option. This is statistics. You can count the number of routes that you are having on this node. Do the same on the other redundant node and ensure that you are getting the exact route information on the redundant nodes. So on UPs, on SPs, you do the routing table checkup just to ensure that you have the necessary routing information. And finally, you also need to do link utilization or congestion checks. So check, how are the links being utilized? Are there any links that are choking? Are there links that are congesting in the network? Are there links that you need to do some upgrade and ensure that you don't have any issues, especially during peak hours or busy hours of the day? So for the link utilization, you can log into the nodes or you can query using the NMS depending on the NMS that you have. For example, I can just display interface gig 0/0/0 and see, like you can see the input bandwidth and output bandwidth. If it's approaching 100%, then it means your link is congested and you need to do some upgrade to ensure that you don't have any issues when the links are highly utilized. So very straightforward, and this one should be done end to end. Whenever you are having issues in the network, you need to do these checks end to end. Don't just do on the UPE. Don't just do it on the SPE. You need to do it end to end, from the BTS to the UPE to the SPE to the NPE and even to the controller itself. You need to do these checks. And one thing to remember, once you've done this test, always remember to restore. If you've shut down a link and you've confirmed everything is okay, ensure you unshut that link, check the status, check the protocols are established, check SIS, check BGP, ensure that the link has been restored, the protocols have established, you are getting the routes information as expected, traffic has restored to the primary link before you do any other checks. Many times, many people end up doing multiple things at the same time. You've shut down one link, you haven't enabled it, you're already going to shut down another link. That one could cause some service impact. So you do one test, you restore, and then you do another test. Once you've completed the first test, the second test, the third test, and all the tests are done, you also need to cross-check and ensure that everything is restored as expected, everything is up, the protocols are up, the links are up, and everything has been restored to the initial state before you close the activity that you are doing. So thank you so much. This is just, of course, there are other tests that you need to perform, and you can tell us in the comment sections which other tests you normally do in the network, and we will be glad to hear from you. So thank you so much for watching this session. I hope you've enjoyed it. I hope they've learned something from it, and again, we'll be having other sessions published on the channel. Please check out the previous session that we've had on the live training, IPRAN training session. There are other lab simulations on the channel, Huawei, Cisco, Juniper, Nokia, and they are just there to help you to understand how to implement and configure, troubleshoot different protocols on different vendors. And I hope it helps you to master these different vendors and the implementation on these different networking devices or networking protocols. So thank you so much for watching this session. Again, just remember to like this video, to comment, to share, and also to subscribe to our channel, and stay tuned in for more upcoming videos. Thank you so much, and see you in the next episode.